Hear me okay? Can anybody not hear me? Yes, that's always the response you get from that kind of question. Okay, I'm going to talk to you about some work we've been doing over the last 10 or so years, which has been sponsored by a number of agencies, including National Police Improvement Agency, the British Academy, and the Home Office. There's lots of stuff that I'm not going to talk about, and I am going to talk quite briefly about each of the things we've been doing, just to give you a broad outline of the kind of work that we've been doing. The sorts of things that we've been looking at are trying to predict future patterns in crime. And there are a number of different questions that we might ask in relation to that. A really simple question that you probably think has already been answered but hasn't is, how do we predict, or can we predict, what level of crime we might have tomorrow on the basis of crime today, yesterday, and so on? Almost no academic literature on that. So we've recently been doing some work where we use techniques from statistical physics, statistical methods like self-exciting point processes to try and make those sorts of predictions. We've also done some work on trends in crimes. So what is actually stolen in crimes, or what is the modus operandi that offenders are using, and are those changing over time? But I'm not going to talk about those two types of predictive tasks. What I am going to focus on instead is the work we've been doing on trying to predict where burglaries are most likely to next occur. And by next, I mean over the next day or the next week. And the work we've been doing focuses on a range of different crime types, but I am going to focus on the crime of burglary for this presentation. So just to give you a very quick overview of what I'm going to do, I'm going to talk about the work we've done looking at spatial patterns of crime, first of all. So what are the sorts of regularities we observe when we look at where burglaries take place? Are there patterns that are useful to us? I'm then going to talk about the work we've been doing on space-time clustering, so where we liken crime to a disease to see whether or not there exist regularities in patterns that would help us predict where crimes might next take place. And then I'm going to briefly talk about a collaboration that we have with West Midlands Police in this case, where we're taking all of the work that we developed to build a predictive tool which they're actually going to field test in a randomized controlled trial over a period of 12 months. So they're going to take half of Birmingham and use this predictive tool and see what effect it has relative to the rest of Birmingham, which isn't using that tool. And then I'm going to finally talk very quickly about the spectre of displacement, which is the simple argument, why bother doing policing over here, because you'll just move it over there. OK, so first things first, for any of you that aren't familiar with crime patterns, just a very simple map. The map on the left is one policing area. The points on the map just show you the distribution of burglary events. And this is over a 5-year period. And what you can see from that map straight away is that there's a kind of clumpiness to it. The points tend to cluster together in space. Now, that may or may not be interesting. The map on the right shows you the configuration of the street network. And what you can quite clearly see is that there are some areas where there simply aren't any houses. So in the case of burglary, if we've mapped the data properly, we wouldn't be expecting many crimes at those locations. But actually, when we analyze this kind of data using spatial point pattern types analysis and more sophisticated means, we do find that this kind of pattern does show spatial clustering above and beyond what we'd expect on a chance basis or given the spatial distribution of households. So we get spatial clustering at the kind of area or point level. More recently, we've been doing work looking at patterns of clustering at the street level. And colleagues in the space syntax that work in space syntax have also been doing work on this topic for quite some time. To give you a sense of that, what we find, the map on the left shows you the rate of burglary per street segment in one policing area. What we find is if we look at the street segments that have the highest risk on them, so that's that highest number of burglaries per household located on them, we find quite a lot of concentration. The street segments that account for 5% of homes account for 40% of the problem. So the question is, if we can identify those street segments that account for a small fraction of homes, we can send resources to those locations, we might be able to deal with a large amount of the problem. And we can show that actually that this concentration is much, much higher than we'd expect on a chance basis. So it does mean something which is useful academically and in operational context. The other thing to note on the map you see here is that if you look at the red lines, so these are street segments with the highest burglary risk, whilst you see that those do tend to clump together in some cases, we also see what we might describe as sharp discontinuities, where we have red lines adjacent to yellow lines. So we've got very high burglary risk street segments adjacent to very low risk burglary street segments. So what that suggests is the area level explanations as to why crime occurs where it does aren't sufficient to explain the actual precise spatial patterns. There's probably something about the street network which is playing a role in where crimes take place. Why might that be the case? So one of the theories that we tend to draw on quite heavily was developed by Pat and Paul Brantingham. Now, crime pattern theory is pretty straightforward. It says that all of us have routine activity nodes, places that we would frequent very commonly. Those would include place of work, where you live, recreational places, shopping, and so on. We frequent these places very commonly, and we travel to and from them along pathways. And the idea, very simple idea, is that as traveling to and from these locations and visiting them, we develop an awareness space of the places we visit and the areas in between. The idea is offenders do exactly the same thing. And actually what we find from offenders is that spatial exploration is really quite rare. So their awareness spaces are pretty much confined to these sorts of locations. The idea of crime pattern theory then is that crime is most likely to take place where offender awareness spaces intersect with good opportunities for crime. Now that leads us to a number of testable predictions. One of which is that we might expect crime to be most likely to take place on those street segments which are intended for moving people through areas to and from particular locations. So we did a study a few years ago where we tested the following hypotheses. That the risk of burglary would be highest on those types of street segments which are intended for high usage. That the risk of burglary would also be highest on those streets which are most connected, so more people would move through them. And that would be particularly the case for the more connected street segments which are connected to major roads. The opposite of that is that the risk of burglary should be lowest on cul-de-sacs, because after all, these should be known to far fewer people, typically only those people that live or visit those locations. And as a secondary part of that, we suggested that risk should be even lower on cul-de-sacs that are sinuous or bendy in nature. So if you have a linear cul-de-sac, so it's a straight line, people can have awareness of that location and the opportunities just by walking past it. If you have a bendy cul-de-sac, it's much harder to see down that location and understand the opportunities that might present themselves. So we did a study. The policing area shown in the map on the right. We started off with a classification developed by the Ordnance Survey. So we looked at roads which are classified as major, minor, the local roads, and private roads. And local roads, because most of you probably aren't familiar with the OS classification, local roads are those kind of residential streets on which houses are typically located. In addition to that, we classified each street segment as whether or not it was a cul-de-sac or not, and whether it was a linear or a sinuous cul-de-sac. It took me 2 days to do that classification, and that's 2 days of my life that I really don't ever want to revisit. It was basically a matter of going through the map and classifying cul-de-sacs either as these linear or these bendy ones. We also used a series of measures from graph theory to actually characterize the street segments, but I'm not going to present that now just to keep things simple. When we look at the patterns in the aggregate, what we find is a pretty clear pattern of results. Those roads which were intended for higher usage or throughput had a much higher burglary rate than did those roads which would be less frequently known to different people. We also found that the sinuous cul-de-sacs did have a significantly lower rate of burglary than did those that were linear in configuration. And where local roads are connected to major roads, they had a higher rate than did local roads that were not connected to major roads. Now, obviously, there are problems with aggregate analysis of this kind, so we conducted more sophisticated, if you like, analysis where we looked at patterns at the individual street segment, and we used a hierarchical linear model. Included in that information about each street segment, what kind of road it was, how many roads it was connected to, the area within which it was located and the demographics of that area. And we also estimated the effects of unknown variables. And we come up with exactly the same pattern of results as you see here. OK, so we demonstrate that crime clusters at the area level. It clusters at the street segment level. We also know it clusters at the location of place, or the unit of place. And place can be defined in a variety of ways. The context of this talk, I mean the individual household. So we find that a small fraction of households account for a large proportion of all burglaries. What we also find, though, is when a burglary occurs, if that household is re-victimized, it tends to occur very swiftly. So we have a simple graph here. Time elapsed between one burglary and the next at an individual household, and the number of burglaries which occur at those different intervals. What you see is very clear exponential decay over time. So when repeat victimization takes place at the same household, it happens very quickly, which is an interesting regularity to observe. Why do we think we see this particular pattern? There are a number of explanations for this, and we have tested all of them, but the most simple is what we refer to the booster count, which is simply that the same offender returns to that household, presumably because they know it's a good opportunity for crime. The reason we suspect they return very quickly is partly because if you return quickly, the conditions are unlikely to have changed, and offenders might be returning to pick up things that they know that they've left behind but can actually sell. In trying to expand this a little bit, so to focus not just on the burgled household, we borrowed some theory from behavioral ecology, in particular optimal foraging theory. The idea of this is that when animals are foraging for resources in the wild, what they seek to do is maximize the benefit of that activity whilst minimizing the risk and keeping search time to a minimum. And we figured that burglars committing repeat victimization would be a good example of this. After all, they'd be returning to households for which they perceive the benefits to be high, the risk to be acceptable, and they'd keep search time to a minimum insofar as they'd be returning to households about which they already knew something. But we also wondered, if that's the case, would they not return to houses on the same street which were near to previously victimized households? After all, they'd share similar characteristics. Similar people live in them. The houses will share architectural features, and so on. So we did a study to actually look at this. What we did is we took 5 years' worth of burglary data for the county of Merseyside. We identified all the streets on which burglaries took place, and we looked at each street where burglaries occurred. And for each of the burglaries on that street, we worked out how far apart they occurred from each other, both in terms of the number of doors apart and how much time elapsed between them. What we found, which is hopefully really obvious from this graph, is that we see what we might describe as space-time clustering. When a burglary occurs on the same, two burglaries occur on the same streets of each other within 1 week, the previously victimized home is most at risk, but then we see a pattern of spatial decay, so that the neighbors of the victimized home are most likely to be at risk than those further apart. So we took that a stage further and came up with an analogy with disease communicability. And we wanted to know whether or not burglary and other types of crime actually spread in much the same way as a communicable disease would. Do they exhibit these sorts of patterns? So we borrowed some techniques from the field of epidemiology designed to detect disease contagion. And the way this works is really quite simple. You take a set of data, such as burglary, and for each event you compare it with every other, and you work out how far apart those pairs of events occur from each other in space and in time, and you populate a spreadsheet something like this one. The trick then is to work out, would we just expect to see these frequencies if the patterns of crime could be explained by the fact that some areas are just more risky than others? Or are these frequencies higher than we'd expect, and do they infer that there might be a process of contagion taking place? To cut a long story short, what we find is when we do these kinds of analysis, no matter which country we do it in or which time period, we find is we get an overrepresentation of burglaries which occur close to each other in space and time, which does suggest there's a contagious process in patterns of crime. And incidentally, we find that for patterns of insurgency in Iraq. We also find it for patterns of maritime piracy throughout the globe. Well, what about the process? Is it the same offenders returning to the same properties? We've recently analysed data for crimes detected by the police. And what we find is if we look at those crimes which occur very close to each other in space and time, they're massively more likely to be the work of a returning offender than are pairs of burglaries which occur close to each other in space but further apart in time, which does suggest returning offender. We've also taken a different approach where we actually interview offenders. So we interviewed just over 30 burglars and asked them how they actually selected locations to commit crime in. I won't show you some of the quotes that we got back from those people. They're quite colourful, but these two examples illustrate what we got back, which are quite typical. If this area I didn't get caught in, I earned enough money to see me through the day, then I'd go back the following day to the same place. If I was in, say, the place and it came on top, and by came on top, I mean I was seen, I was confronted, or I didn't feel right, I'd move areas straight away. And that was a pretty common response that we got from the offenders, that they go to an area, commit a series of offences, and move on when they perceive the risk of apprehension were too high. Okay, excellent. So all this leads us to the fact that we've identified regularities in crime patterns, this space-time clustering. We've got some understanding of the mechanism which actually generates these patterns. So basically, we ought to be able to predict these patterns of crime, was the premise we started with back in 2004. Just to sort of summarize what we've got in a slightly different way, what we think happens is when a burglary takes place, risk spreads to nearby locations, but that risk decreases over time. A series of offences taking place, they'll each spread risk, and so on. So we ought to be able to take that sort of process and build models which will predict where crimes next occur. We can do that in two ways. One of the ways that we've done this is to build computer simulations to test whether or not it's the case that when we implement those sorts of patterns, do we, in the computer simulation, generate patterns as observed in the real world? And we've done computer simulations of varying degrees of sophistication, and pretty much what we find is we do get the same sorts of patterns as we see in the recorded crime data. The other approach is to build forecasting models. So you take a study area of some kind, and typically what we do is we divide it into a grid of regular-sized cells, and we make predictions for each of those cells. We take a training data set, build a statistical model, and we apply that statistical model to forecast for in the future. To cut a long story short, when we do that, basically we have models which outperform very simple models of crime mapping where we just calculate the density of crime in the recent past. So policing often relies on saying, in the past, these are locations where crimes have occurred, therefore this is where they'll occur in the future. What we find is where we use these slightly more sophisticated models, we get more accurate predictions of where crime occurs in the future. Very quickly, does crime displace? If you target a particular location, no. In fact, you get the reverse. You're more likely to reduce crime in a location and diffuse positive benefits to nearby locations. Finally, just to summarize, basically what we found is burglary is more likely at certain locations, and there are regularities at the types of places it is likely to take place. Crime is more likely on connected segments, connected street segments. We also find there's a contagious nature to patterns of crime. The types of analysis we've done so far look at point patterns of crime. They don't look at how crime diffuses through a network. So the work we're doing at the moment seeks to combine those two particular approaches. And Toby Davies in particular is building mathematical models and simulation models to test this. And as I said, the aim is then, once we've built those, is to try those out in a real-world operational context to see whether or not they have utility for the police. Final thing, on a totally different scale, we have a poster outside. We have an EPSRC-funded project which looks at global dynamics. I won't say anything about that because I've overrun, but it is outside if you want to see it. Thank you very much.